Is it really possible to build a diffusion model in just 215 lines?
Hi everyone, I'm Matthew. I have built this simple and optimized code that actually gives a very good result. It works with the MNIST dataset, and you can even generate custom numbers. If you are interested in learning about AI models, stick around and watch the rest of the video with me.
I thought maybe a demo helps, so this is my model's demo.
So let's start with the basic imports that we need for building our diffusion model. First, we import Torch. Torch is the core library for deep learning in Python. Then we import torch.nn and torch.nn.functional, which gave us the tools to build neural network libraries and Activision functions. Next, we import data loader so we can load our dataset in batch. After that, we use torchvision.transforms to pre-process images, and we import the MNIST dataset directly from torchvision.datasets. I also import MNIST. This library makes training easier on monitor. And finally, I import math for a few small calculations we'll need later. These imports basically prepare everything we need to build the unit, the diffusion process, and the training loop. Here, I'm creating a sinusoidal positional embedding class. This module takes a time step and turns it into a vector using sine and cosine. In the constructor, I just save the dimension of the embedding. And inside the forward method, I first get the device of the input time. Then I split dimension in half, because half of the values will use sine and the other half will use cosine. Next, I compute a set of frequencies using an exponential formula. Then I multiply those frequencies by the time step to get the raw positional values. I apply sine and cosine and concatenate them together. This gives the model a way to understand where in the diffusion process each step is. This residual block takes the feature maps and processes them through two convolutional layers. First, I build a small MLP to transform the time embedding so the block can react to the current diffusion step, using group norm and pass it through the first convolutional layer. After that, I applied another group name and sent the output through a second convolution. I also add dropout to make the model more stable during training. This block uses gloop as the Activision function to keep everything smooth and normalized and non-linear. Here I'm checking if the input and output canals match. If they don't, I create a shortcut using a convolution. If they do match, it's just an identity connection. This whole structure helps the model learn deeper features without losing information along the way. In the forward path, I first normalize the input, apply gloop, and send it through the first convolution layer. Then I take the time embedding, pass it through the MLP, and reshape it so it can be added to the feature map. Next, I normalize the result again, applying gloop and run it through the second convolutional. I apply dropout here to keep the model from overfitting. And finally, I add the shortcut connection to keep the original information flowing through the block. Here I'm building the main architecture that the diffusion model will use. First, I store some basic parameters like the number of the input, channels, and the feature size. Then I create the sinusoidal time embedding module, which tells the network what diffusion step it's at. Next, I set up the first convolution layer, followed by group norm and zero activation to clean and shape the input. After that, I add the first residual block for the downsampling path and the max pooling layer to reduce the spatial resolution. Then I build the second residual block with stable features and another pooling layer to go even deeper into the network. In the middle of the unit, I place two residual blocks that act as the bottleneck and layer the most abstract features. Here I'm creating a small MLP to embed the class condition, so the network can generate digits based on the label we give it. Here we are on the unsampling part of the unit, basically the decoder part. First, we use conv transpose layer to scale the feature maps back up. After each unsample, we run a group norm and a G loop just to keep things stable and help the feature flow smoothly. Now, every time we go up, we also bring down the matching. Features from the encoder and concatenate. Features from the encoder and concatenate them. That's why each residual block takes n feet. That's why each residual block takes n feet as input. Half for encoder, half for decoder. So this is for our path of the whole unit. First things we do is handling the context. We embed the class vector, and if mask says ignore it, we basically zero it out. Then we grab the time embedding, scale it a bit, and add the two together. That gives the model both when we are in the diffusion process and what class we are conditioning on. We push the input image through the first conv layer to get our initial features. Next, we push the input image through the first conv layer to get our initial features. Then we start going downsampling. The first residual block processes the features. Then we downsampling them. In the residual block, we hit two residual blocks back to back. This is where the model mixes everything together. The time info, the class info, and the deep visual features. Now we start going back up. We unsample, normalize, active, and then we concatenate the matching features from the encoder. That skip connection helps us bring back grain details we lost during downsampling. We run a residual block to blend everything nicely. Then we repeat the same thing for the last stage. Unsample one more time, bring back the early features from the beginning, concatenate them, and process them with another residual block. And finally, we push everything through the output conv layer, and that becomes the predicted noise for this diffusion step. This is the setup part of the diffusion model. We choose how many steps we want, and then we build the beta schedule, basically the noise. If it's linear, we just go from a teeny beta to a bigger one in a straight line. If it's cosine, we use that smooth cosine. That gives nicer noise behavior. In both cases, we end up with a list of betas that tell the model how much noise to add at each step. So this is the part of the diffusion model. So this is the setup part of the diffusion model. We choose how many steps we want, and then we build the beta schedule, basically the noise. If it's linear, we just go from a tiny beta to a bigger one in a straight line. If it's cosine, we use that smooth cosine. In both cases, we end up with a list of betas that tell the model how much noise to add at each step. After After we pick the betas, we turn them into alphas and then alpha bar, which are basically the total noise level up to each step. The forward process just adds noise to the clean image. We grab a random noise tensor, scale the original image by the alpha bar. This is where the model starts turning pure noise into real image. First, we make a completely random noise image. And then we prepare the class labels and one-hot encode them. Now we enter the main loop. From the last step down to 0, each step we call the main twice. Once with context, conditional, and once without, unconditional. We mix these two predictions to get the classifier-free guidance. Which helps the model focus better on the target class. We subtract the predicted noise from our correct image, and if we are not at the final step, we add a bit of fresh random noise. We repeat this step by step until the pure noise gradually turns into a clean image. Okay, so here we set up the training. First, we check if we have a GPU and use it if we can. Then we define some basic parameters like epochs, batch size, feature size, and learning rate. After creating our unit model, we wrap it inside the diffusion model with a cosine betas schedule. We also set up the Adam optimizer to update the model's weights. For the data, we load MNIST, convert the image tensor, normalize them, and put them into a data loader batch to the model. Let's talk about the actual training loop. For each epoch, we set the model to training mode. We go through the dataset batch by batch using a progress bar. For each path, we zero the gradients and move the image and label to the GPU. The labels are one-hot encoded, and we randomly pick a time step for each image. We also randomly mask some context with a small probability for classifier-free guidance. Then we add noise to the image using the forward diffusion process. Next, the model predicts the noise, and we compute the MSE loss between the prediction and the actual noise. We backpropagate, flip the gradients to keep them stable, and then update the model with the optimizer. After each epoch, we save the model's weight. We also sample a few images from the diffusion model, scale them to 0.1 and save them as PNG. This way, we can actually see how the generated image improves over time. Thanks you for watching my video.